Hey guys, in this video we're going to keep going with stoichiometry and get into the actual full process of stoichiometry where we're applying all of the conversions we learned in mole, so going from moles to particles, liters, and grams, along with our mole to mole conversions we learned yesterday to do conversions using balanced chemical equations. Some of these might just end up being one-step problems. They might be two, three, or four-step problems. But it's all using the exact same skills that we've learned. So this video is really just going to consist of a bunch of different examples that we're going to work through together so you can see this process and then try it out for yourself. Whenever you're thinking of doing multi-step calculations, you want to make sure that you have a balanced chemical equation first. You always want to convert the given substance into moles, convert into moles of the other substance using mole ratio, and then convert the new substance into whatever your new unit is. Where we had looked at our mole roadmap, you can also use a double mole roadmap to represent stoichiometry. So remember, we could convert moles into grams, liters, or particles. Well, you can put a second one next to it, converting into grams, liters, and particles. And now, knowing that mole ratio, you can use that as a conversion. So this may help you if you're getting stuck on what steps to do next. So say that you wanted to go from liters of one substance into grams of another. You would say, okay, I need to go from liters to moles, then moles of one substance into moles of another, and then moles of one substance into grams of another. So that would be one possibility. And I'm going to highlight that in yellow. Um, if we wanted to go from particles of one substance to liters of another, I'm going to highlight this in orange. We'd say, okay, we need to go from particles to moles, moles to moles, and then moles to liters. So this may help you figure out how many steps you need to take and which steps are appropriate to take as you're going through stoichiometry problems. So feel free to sketch this out for yourself and reference it as needed. Here's what some of our problems are going to look like. So yet again, you're going to have an actual equation, but you really need to figure out what steps you need to take and then perform those conversions. So here we have nitrogen and hydrogen producing ammonia, and we want to calculate the number of grams of ammonia produced by the reaction of 5.40 grams of hydrogen with an excess of nitrogen. Anytime it says there's an excess of something, that's simply extra information saying that this reaction can go to completion. So if need be, feel free to kind of use that mole roadmap to figure out what steps you need to take. So here it's giving us grams of hydrogen. So we would go from grams to moles. We're going to have to go from moles of one substance into moles of another substance. And then we're changing into grams of ammonia. So that's the part that would be highlighted in our little stoichiometry roadmap if needed. Excuse me, I drew that too low on my screen. So you're always still going to start with what is given. So we are given grams of hydrogen. And we're looking for grams of ammonia. So we are going from grams of one substance into grams of another. Now we simply have to keep canceling out units until we get to the unit needed. So we no longer need grams of hydrogen, so that can go on the bottom. Our first step in our roadmap was to get to moles, so that would be our first conversion that we can use. So first step is always to get to moles. Remember, grams per mole is molar mass from our mole unit. It's 1 mole is equal to the molar mass. Do remember that hydrogen is diatomic. It is H2. So our molar mass is 2.016. We're going to cancel out grams of hydrogen, and that leaves us with moles of hydrogen. Well, we're looking for grams of ammonia, so we actually don't need anything dealing with hydrogen anymore. So we need to get rid of moles of hydrogen, so that will move to the bottom. And since we're looking for grams of ammonia, we first have to know moles of ammonia. So this is that mole to mole conversion that we learned yesterday. So according to our balanced equation, that's where we get our mole ratio from. We have 3 moles of hydrogen and 2 moles of ammonia. That will cancel out moles of hydrogen, leaving us with moles of ammonia, but we're not finished because we want grams of ammonia. So since we no longer need moles of ammonia, that will go to the bottom to change into grams of ammonia. Remember, grams per mole is molar mass, and it's always out of 1 mole. And to find molar mass, you need to add them together. Nitrogen has a mass of 14.01 plus 3 hydrogens that are 1.008 apiece for a molar mass of 17.034 grams. So that will cancel out moles of ammonia, leaving us with grams. So we're ready to punch in the calculator. So we're going through the exact same process, but our problems may be a little bit longer. Remember, any number above the line you multiply, any number below the line you divide. So we're going to do 5.40, divide by 2.016, multiply by 2, divide by 3, and multiply by 17.034. Now, some people like to multiply everything on top first and then go back and divide by everything on the bottom. That's perfectly fine. As long as you do the correct function with the correct number, it doesn't matter the order that you punch them in the calculator. So your calculator answer gives you 30.418 grams. In terms of sig figs, our original number given had 3 digits, so we want to make sure our answer has 3 digits. So we're going to round this to 30.4 grams of ammonia. And that is the entire process of stoichiometry. It's just putting all of the smaller steps that you already know how to do into one larger step. The rest of this video will be more practice problems. Feel free to watch as many as you feel you need to before going on to practicing. In this problem, we have calcium carbide and water producing ethine and calcium hydroxide. So the acetylene gas, or the ethine, is produced by adding water to calcium carbide. How many grams of acetylene are produced by adding water to 5 grams of calcium carbide? Yet again, start with what is given. So we are given 5 grams of calcium carbide. Our first step is always to get into moles. So since we no longer need grams of calcium carbide, that will go on the bottom. We'll change into moles on top. Remember, grams per mole is molar mass, so we'll add that together off the periodic table. Calcium is 40.08. plus 2 carbons, and carbon is 12.01. So that's a molar mass of 64.1 grams. That cancels out grams of calcium carbide, leaving us with moles. Our answer is dealing with acetylene, so we no longer need calcium carbide. So we can get rid of moles of calcium carbide by moving it to the bottom. And we can change into moles of acetylene on top. Mole to mole ratio, remember we get our number from our balanced equation. Always go back and double check that it's balanced. This one is balanced overall. There's 1 calcium, 2 carbons, a total of 4 hydrogens, and a total of 2 oxygens. So with our coefficients for acetylene and calcium carbide, they are both 1. That cancels out moles of calcium carbide, leaving us with moles of acetylene. But we're looking for grams of acetylene, so we need to do one more step. We no longer need moles of acetylene, so we're going to move it down to the bottom and change into grams of acetylene. So remember, grams per mole is molar mass. So we have 2 carbons that are 12.01. Add to that 2 hydrogens that are 1.008 apiece. And we have a molar mass of 26.036 grams per mole. That cancels out moles of acetylene, leaving us with grams of acetylene. So now we can simply put this in the calculator. So we have 5 grams. We're going to end up dividing by 64.1 and multiplying by 26.036. So our grams answer that our calculator gives us, and because we have 3 digits in our original number, we need to round to 3 digits. It's going to be 2.03 grams of acetylene. Let's keep going. Here we have the same reaction, but now we want to figure out how many moles of calcium carbide are needed to react completely with 49 grams of water. So always pay attention to where you're starting and where you're ending, because you won't always have those 4 steps. You may stop short of that. So always start with what's given. We're given 49 grams of water. And we're looking for moles of calcium carbide. Our first step is always to get to moles. So we no longer need grams of water. That will go down below. And we can change into moles of water. Remember, grams per mole is molar mass. We have 2 hydrogens that are 1.008 apiece, and oxygen is 16. So the molar mass is 18.016. That cancels out grams of water, leaving us with moles. But we're looking for moles of calcium carbide, so we need to get rid of moles of water, so we'll put it on the bottom. And we can change into moles of calcium carbide using our mole ratio. There's 1 mole of calcium carbide compared to 2 moles of water. That cancels out moles of water, and now we have moles of calcium carbide, which is what we were looking for. So we are finished right now. We have the appropriate unit. We simply have to put this in the calculator. So we have 49.0 divided by 18.016 divided by 2. Our original number had 3 digits, so our answer should have 3 digits. So we're going to round this to 1.36 moles of calcium carbide. Let's move on to the next one. Here we have water being decomposed into hydrogen, oxygen, and we want to know how many molecules of oxygen are produced when a sample of 29.2 grams of water is decomposed by electrolysis. So start with what is given. So the 29.2 grams of water, and we're looking for molecules of oxygen. So first step is always to change into moles. We no longer need grams of water, so it will move down to the bottom to change into moles. Remember, 1 mole is equal to the molar mass of water, which we just used in the last problem. That was the 18.016. That cancels out grams of water, leaving us with moles. But we're looking for molecules of oxygen, not moles of water, so we need to keep going. Since we no longer need moles of water, that will move down to the bottom, and we will change into moles of oxygen. So, and remember, you need to abbreviate moles and molecules differently. So mole to mole is our mole ratio. So according to our balanced equation, we have 2 moles of water and only 1 mole of oxygen. That cancels out moles of water, leaving us with moles of oxygen, but we're looking for molecules, so we need to do one additional step. We no longer need moles of oxygen, so it's going to go down to the bottom. And remember, molecules is a type of particle. So 1 mole is equal to the 6.02 times 10 to the 23rd particles. That cancels out moles of oxygen. And now we have molecules, so we're ready to put this in the calculator. Remember, when you're typing in that 6.02 times 10 to the 23rd, make sure to use parentheses or the EE button. So we have 29.2 divided by 18.016 divided by 2 multiplied by the 6.02 times 10 to the 23rd. Our original number had 3 sig figs, so let's round our answer to 3 sig figs. And we're going to have 4.88 times 10 to the 23rd molecules of oxygen. All right, let's do another one. How many molecules of oxygen are produced by the decomposition of 6.54 grams of potassium chlorate? So start with what's given. We have 6.54 grams of potassium chlorate. Our first step is always to change into moles. So we no longer need grams of potassium chlorate. It will go down to the bottom to change into moles. Remember, grams per mole is molar mass, so we need to add the masses off the periodic table. Potassium is 39.10, plus chlorine is 35.45, plus 3 oxygens that are 16 apiece, is a molar mass of 122.55. That cancels out grams, leaving us with moles of potassium chlorate. We're looking for molecules of oxygen. So we no longer need moles of potassium chlorate. That will go down to the bottom. We can change into moles of oxygen up top. Mole to mole is molar mass, or excuse me, mole ratio. So according to our equation, we have 3 moles of oxygen per every 2 moles of potassium chlorate. That cancels out moles of potassium chlorate, leaving us with moles of oxygen, but we're looking for molecules. So we're going to do an additional step. Moles of oxygen will go to the bottom. Molecules will go up top. So remember, I'm not sure what happened with my pen. 1 mole, excuse me, of oxygen is going to be 6.02 times 10 to the 23rd molecules. So that will cancel out moles of oxygen, leaving us with molecules. So we need to put this in the calculator. So we're going to have 6.54 divided by 122.55 times 3 divided by 2 times 6.02 times 10 to the 23rd. Our original number had 3 sig figs, so we'll round to 3 sig figs. That's going to be 4.82 times 10 to the 22nd molecules of oxygen. That I feel is enough examples. I may record another video with more examples if needed, but practice using this same process with your practice problems.